Okay, hello everyone, in a new video. So we have reached part 4 of chapter 8, which is the chapter of Newton's second law for rotation for grade 11 students. So we have reached exercise number 4, in which they are telling me a 4 kilogram uniform beam. Then the mass is given by 4 kilograms. By uniform beam, it means that the mass is distributed uniformly along the beam and 1 meter long. So AB is equal to 1 meter, representing the length of the beam, is free to rotate around a fixed axis delta, passing through a point C 20 centimeters away from A. So here, let me make it clear. So the point C represents the axis of rotation. This is important because whenever we are calculating the moment, the distance from the force or the tangential component is measured from the axis of rotation and not from the center of gravity. So let me say that AC is equal to 0.2 meters. While the beam is making a 30 degrees angle with the horizontal, we apply two forces F1 and F2 such that F1 is perpendicular to the beam and its magnitude is 10 newtons. So the magnitude of F1 is equal to 10 newtons. And F2 makes an angle alpha is equal to 30 degrees. And we have that F2 is equal to 15 newtons, and take it G is equal to 10 meters per second square. Now, this is the horizontal direction, okay? So, at all points of the beam, we can consider infinite lines corresponding for the horizontal. Now, in number 1, they are asking me to calculate the moment of each force. So, the force F1, F2, and the weight of the beam W and the rotation around the rotation of the axis delta. And sorry, we have F1, F2, the weight, and the reaction of the axis delta. So how many forces do we have? We have F1, F2, the weight, and the reaction around of the axis delta. So only F1 and F2 are being represented. Now let me represent the force, which is the weight. Now the weight, it is classified as a force acting at a distance, so the point of application will be the center of gravity G, like this. So this is the weight W. As for the reaction, in this case, the line of action, so the reaction is a contact force. The point of application will be the point of contact C, which is between the beam and the axis of rotation. So between the beam AB and the axis of rotation. So the reaction will be somewhere here like this. We don't know specifically the line of action and the direction of the reaction. So this is not important. Let's consider it to be something like this, say, for example. Okay, it's not important. Now we need to calculate the moment of three forces F1, F2, W, and R. Let's start by the moment of the force F1 around the axis delta, which is equal to F1 tangential multiplied by the distance d. In this case, d is equal to the distance from F1 to the point C, which is given by AC, which is equal to 0.2 meters. Now F1 tangential, here let me choose the positive direction, which is like this. Now notice that F1 will try to rotate the beam around C like this in the negative direction, times the magnitude times the cosine of the angle. So if this is the radial direction, then the tangential direction will be like this. Notice that in this case F1 is completely lying along the tangential direction, then no need for a cosine. So the moment of F1 around the axis delta is equal to minus this replaced here. So minus F1 multiplied by d, which is equal to minus the value of F1, which is equal to 10, multiplied by 0.2, which is equal to minus 2 Newton meter, because the unit of the moment is given by Newton meter. This is F1 around delta. Now what about the moment of the force F2? So it's given by F2 tangential multiplied by D. This is a component. It may carry a positive or a negative sign. So the distance C between F2, the point of application of F2, and the axis of rotation is given by CB. We don't know the length of CB, but CB is given actually by AB minus AC. If AB is equal to 1 and AC is equal to 0.2, so this is equal to 0.8 meters. Now F2 tangential, this is the radial direction, which is this, and this is the tangential direction. So now notice that F2 will try to rotate the beam around the positive direction like this. So it is a plus multiplied by F2 multiplied by the cosine in which F2 makes with the tangential direction. If this is alpha, and that this is pi by 2 minus alpha, which is equal to F2 sine alpha. And now the moment of the force F2 around the axis delta is equal to, replacing this here, so it is F2 sine alpha multiplied by D, which is equal to F2 is given by 15 multiplied by sine of 30 multiplied by the distance D, which is 0.8. Let me use the calculator to calculate this value. Then this is given by 60 newtons meter. So let me write here that the moment of the force F1 around delta is equal to minus 2 newtons meter. The moment of the force F2 around delta is equal to 60 newton meter. Now what about the moment of the weight around the axis delta is given by the tangential component of the weight multiplied by D, knowing that D is the distance between the axis of rotation and the point of application of the force, which is CG. Now notice that CG, so how can one calculate the distance CG? So D is equal to CG, which is AG minus AC. So this distance here is this distance minus this. Okay. Now why so? Because we know that since G is the center of gravity and the mass is distributed uniformly, and this is equal to AB over 2 minus AC, and AC is given by AC. So this is 1 over 2 minus 0.2, which is equal to 0.5 minus 0.2, which is equal to 0.3 meters. Now we can check that if AC is equal to 0.2 meters, and this is 0.3 meters, and GB is equal to 0.5 meters because it is a half of the 1 meter. Now all of these together, they add up to 1, which is the length of the beam. Now the tangential component of the weight, let's see. This is the radial direction connecting C and G. This is the tangential. So notice that the weight will rotate like this around C in the negative direction, multiplied by the magnitude of the weight times the cosine of the angle between the weight and the tangential direction. So here we need to work a bit in geometry. So we are interested in determining this angle here. This is a bit tricky. So for this reason, let me consider here another direction, which is the horizontal. And now let me erase this reaction. I will consider it later, just to make the figure more clearer. Now, why I have plotted this line? Because this angle here is between this line and the beam. So, and we have this another line. So in order to make use of properties related to the corresponding and alternate interior angles, we need to have two parallel lines in which one line intersect them. So now we have, so this is a parallel line, this is another parallel line, and we have one line intersecting them, which is this. So notice that this angle alpha is the same as this angle alpha here. Okay, so this angle is alpha, but notice that this angle is 90 degrees, which means that this angle is also 90 degrees. So if this is 90 or pi by 2 and this is alpha, then this angle here will be pi by 2 minus alpha. So this angle here is given by pi by 2 minus alpha. Okay, and imagine that, how can one verify that this value is correct? Imagine that if the rod is now completely horizontal like this, so F2 will be like this, so the angle of alpha is given by 0 in this case. However, the weight will be vertically downward like this. So if alpha is 0 here, then this is completely pi by 2. Okay, so so here the trick is given by to consider a line parallel to F2 passing through the point of application of the weight. So whenever it's a bit tricky to determine the angle, then consider another line parallel to the line of action that give us the angle in order to determine the angle between W and the direction that we are interested in. However, if we refer back to our problem, we are interested in determining the tangential component. So we need the angle between W and the tangential direction. If this is pi by 2 minus alpha, then this angle is alpha. So cosine alpha. Okay. Now, as for the moment of the weight around delta is equal to, so replacing this here and this here, we get that minus W cosine alpha multiplied by D, which is equal to minus the weight is given by M multiplied by G multiplied by cosine alpha, which is given by cosine 30 multiplied by the value of D, which is 0.3. So minus the mass, which is 4, multiplied by 10 cosine 30, I think it's given by radical 3 over 2. Let me check. Yes, multiplied by the value of D, which is given by 0.3. Plugging these values on the calculator, so the moment of the weight W around the axis delta is given by, let me just do the computation. It's given by almost 10.39 Newton meter. So minus 10.39 Newton meter. Okay. Now what about the moment of the reaction force around the axis delta? So this is the reaction, something like this. Now we can remove these. Now the moment of this force is equal to 0. Simply line of action passing through delta. So no tangential direction, it's completely radial. So the moment of the reaction force around delta is equal to 0. Now in number 2 they are asking me to show that the beam is not in equilibrium. So in order to show that the beam is not in equilibrium, we need to calculate the sum of moments around delta, which is given by the moment of the weight around delta plus the moment of R around delta plus the moment of F1 around delta plus the moment of F2 around delta. So this is minus 10.38 plus 0. Okay, just let me check something. So this is negative, F1 negative, yes, okay, plus the moment of F1, which is given by minus 2, and the moment of F2 is given by plus 6. Now on the calculator, minus 10.38 minus 2 plus 6 is equal to minus 6.38 in Newton meter, which is different than 0. Okay, since summation of moment around delta is different than 0, then the beam is not in equilibrium. And the thing is that because it is not in equilibrium, and because the value of the summation of moment is negative, so this beam will try to rotate in the negative direction like this. And this is reasonable because the effect or the action of W and F1, as in terms of moments, they are stronger than F2, so it will rotate in the direction, in the clockwise direction. And now in number 3 they are telling us, in order to make the beam in equilibrium, we apply a new force F3 perpendicular to the beam at the point A 30 centimeters away from B. So here they are telling us that in order to make the beam in equilibrium, we apply a new force F3 perpendicular to the beam at the point E 30 centimeters away from B. So the point of application of this force F3 is given by the point E. So what's the location of E is 30 centimeters away from B. So let's locate the point E. So this is the point E, in which EB is equal to 0.3 meters. So let me write here EB is equal to 30 centimeters corresponding to 0.3 meters. So the force F3 is applied perpendicular to E, either like this or like this. Okay, so there are two possibilities in which F3 is perpendicular to the beam. They didn't specify in which direction it is perpendicular, but the line of action, it means that it is perpendicular to the beam. Now in part A, they are telling us indicate with a justification the direction of rotation due to F3. Now making sure that now the beam is in equilibrium. Okay, now from part 2 we have determined that the beam is not in equilibrium, and we have justified why it is rotating like this. Now in order to oppose the effect of this rotation and to balance the beam to be in equilibrium, so the F3 must try to rotate the beam in the positive direction, so it must be like this. So in this case the direction of rotation of F3 is clockwise. So let's say since the sum of moments around delta is negative, which means rotation occurs in the clockwise direction, then the direction of rotation due to F3 must be, so if this is clockwise, then it must be anti-clockwise. Here clockwise is one word. In order to balance, and by the balance I mean the equilibrium, the beam. So in this case, now we have specified the direction. The line of action is perpendicular to the beam. The direction will be something like this. For sure, these are not drawn to scale. Now here, let me also write that the sum of moments around delta previously is given by minus 6.38 Newton meter. Now in part B, they are telling us calculate F3, the magnitude of F3. So since we are talking about rotational equilibrium, the magnitude of F3 appears in the new summation of moments. Okay, let me say since, or at equilibrium, at rotational equilibrium. We have summation of moments around delta is equal to 0. What are the different moments in this case acting on the beam? We have the moment due to F1 over delta plus the moment of F2 around delta plus the moment of F3 around delta. Sorry, let me write first the weight, plus the moment of the reaction R around delta plus the moment of F3 around delta, which is equal to 0. Now this is the additional moment that you are interested in calculating. If we are able to calculate the value of this moment, then we can directly deduce the value of F3. Now these, no need to calculate again because nothing changed, and this is pre-calculated, and this is given by minus 6.38 plus the moment of F3 around delta. Now the moment of F3 around delta is equal to 6.38 Newton meter, but at the same time we know that the moment of the force F3 around delta is equal to F3 tangential multiplied by the distance d. Now F3 tangential is equal to, so it will try to rotate in the anti-clockwise, so it's positive, F3 multiplied by the cosine of the angle. So notice that if this is the rotational, this is the tangential direction, so no need for the cosine. So this is equal to F3 multiplied by the distance d. D is the distance separating the point of application and the axis of rotation, which is C. Now, now D is equal to the distance from C to E. Recall that always the distance here that we are implementing is the distance between the point of application of the force and the center of rotation. Now, what about CE? C is equal to the distance CG plus CGE. This we have calculated previously and it's given by 0.3. Now, what about the GE? GE is the distance, is the difference in the distances GB minus BE. And this is equal to 0.3 plus GB is AB over 2 and BE is given to be 0.3. So this is equal to 0.3 plus 0.5 minus 0.3, which is equal to 0.5 meters. Okay, so here this is given by 1 divided by 2 is 0.5. This will cancel out with this, and the distance is given by 0.5. So it is given by f3 multiplied by 0.5. Now here I didn't place any unit because it is expressed in terms of another quantity. Now recall that we are interested in determining the magnitude of f3. So comparing these numbers, because they are equal, we get that f3 multiplied by 0.5 is equal to 6.38. Then f3 is given by 6.38 divided by 0.5. Then it's given by 12.76. Everything is expressed in the SI, so the value of f3 will be in the SI, which is in newtons. As for the next exercise, this is extremely important. Now, in this exercise, we will see how one can determine the value of the reaction between the rod and the support. Now, a uniform 10 kilogram beam, so the moment or the instant the beam has a mass, it will be directly subjected to the weight, although if it's not stated in the problem, of length 1 meter, so the length of the beam AB is equal to 1 meters, is able to rotate around a fixed axis delta, passing a hinge at A. So this is the axis of rotation delta. This is the first thing that we should notice. Point C 30 centimeters away from B, so CB is equal to 0.3 meters, carries a 25 kilograms load by means of an extensible by means of a massless wire. So this mass is given by 25 kilograms. In order to maintain the beam in equilibrium while making an angle alpha is equal to 60 degrees with a horizontal, we attach it to a horizontal string as shown in the adjacent figure. Number 1. Determine the tension T1, the magnitude of the tension in the wire attached to the load. So they are asking me about the tension here. So now in this case, because we are interested in this tension, now here we have two tensions. We have the tension T1 like this, and we have the tension T1 prime like this. And because we know that this string is, they didn't mention an extensible, but it is an extensible, since, okay, now they are equal because it is inextensible, but no need to consider all the system. We can consider only the system which consists of this solid and this string in order to apply the condition of equilibrium to determine the value of T1. So here we have that M is equal to 25 kilograms. We have the weight acting vertically downward like this. And the tension acting vertically upward like this. So this is the tension T1. We can directly say at equilibrium. Here we are talking about translational equilibrium of the solid, of the solid S. Now we have that weight, sum of forces is equal to 0. Weight plus tension is equal to 0 vector. So W is equal to minus tension. Here no need to project anything because this is a vectorial equation, only consists of two vectors. So in magnitude, here we are talking about the weight of the solid. Let me specify that this is a solid S. So Ws is equal to the tension T1, but the value of Ws is equal to M multiplied by G. Here take G is equal to 10 newtons 10 meter per second square. So 10 multiplied by 10, which is equal to 100 newtons. Then the tension T1 is equal to 100 newtons. So we have the tension T1 is equal to 100 newtons, and let me specify that this is the tension T2 and this is the tension T1, which is equal to the T1 here. Now let me remove the vector, because we cannot say here that this, if we need to place a vector here and here we need to place a prime, because these are not two equal vectors, they have opposite directions. But if you are discussing without magnitudes, they are equal, and in magnitude they are equal because the string is inextensible. Now they are telling us find T2, the magnitude of the tension in the horizontal string. Now here we are interested in determining the tension T2. So it is at equilibrium. Then in this case we can use two types of equilibrium that is given by the translational and rotational. Here which mass we are considering? We are considering the beam. So we can consider only the system that is subjected to which forces? To the tension T2, to the tension T1, and to the reaction at the point A. So how many forces do we have? We have the tension T2, which is acting, for example, horizontally to the left. We have the tension T1 acting vertically downward. Sorry, we also have the weight of the beam, which is along the center of gravity downward like this. And we have the reaction at the point A. So let me also represent, so suppose that this is the center of gravity G of the beam, and this is the weight acting vertically downward. Now here we don't consider anymore the weight of the solid as this is not considered anymore, because we don't care about what's causing the tension along this string. What we care about is that the value of this tension is given by 100 newtons, and we don't care about what is causing this tension. So simply we can eliminate this system after we have determined that the value of the tension due to this system is given by 100 meters. It is completely wrong to consider again the value of the weight of the solid and the tension which is opposite to the tension that we are now interested in. So let's eliminate all of these. So now simply the system reduces to, or the forces acting on the beam are given by T1, T2, the weight, and the reaction at the point A. Okay? So we don't know the reaction at the point A. Suppose that the reaction is something like this. Okay? Now we are interested in determining the value of this tension. So let me place it in a box. And for sure we need to use the condition of equilibrium to determine the tension T2. Let me do the following, because this is the first time that we solve exercises of this type. Now for sure we need to use the condition of equilibrium to solve for T2. So by equilibrium, we are talking about two equilibriums that are given by the sum of forces is equal to 0 factor and by the sum of moments is equal to 0 around a specific axis, which is in this case delta. Usually the way that we proceed in such type of problems is that we solve this first, then we solve this second. Why? Let me write both equations and discuss each of them. So for the first equation, which is given by 1, the sum of moments will be given by the moment of the tension T1 along delta plus the moment of the tension T2 around delta, the moment of the weight around delta, and the moment of the reaction R around delta. Eventually, no need to place this term because this term will always vanish. So here, what are the unknowns in this case? The unknown is given by the tension T1 and the reaction R. So no need to write this term because this term will be what? Will be 0. Okay. As for the equation 2, it's given by the tension T2 plus the tension T1 plus the weight plus the reaction R, which is equal to 0. Now this is a vectorial equation and we know how to deal with it. But the thing is that if we need to solve this equation number 2 and we need to project it, so projecting it along the x, projecting it along the y will give us two equations, but the number of unknowns in this case are given by more than 2, because here we don't know this force and we don't know this force. So we cannot solve using this equation to determine T2 and R. So what we will do that, we will use this equation in order to find the value of T2, because here the only unknown is given by T2. We know everything regarding T1 and we know everything regarding W. After we have determined the value of T2, then we will refer back to this equation. We know the value of T2, we know the value of T1, we know the value of W, then we will determine the value of R. Simply, we will always refer to the sum of moments first, then the sum of forces, because we will always gain the fact that there is a force always being eliminated, because the reaction force at the hinge is being eliminated because the line of action of the reaction is always passing through the axis of rotation. So we will proceed in this way. Always keep in mind that we will use the sum of moments, then we'll use sum of forces. But this doesn't mean that this can be generalized. Always think about these two equations together. 90% of the cases we make use the sum of moments than the sum of forces. But this is not a general rule that we can follow always. So we always should consider these two equations, and depending on the number of unknowns, we will proceed. So without further ado, we need to determine the T2, the magnitude of the tension. So let me say at rotational equilibrium. We have the sum of moments around the axis delta is equal to 0. Here we are talking about the moment of the tension T2 around delta plus the moment of the tension T1 around delta plus the moment of the weight around the axis delta plus the moment of the reaction R around the axis delta, which is equal to 0. Now we need to determine the moment of each force and plug it in this expression. Now let's start by the moment of the tension T2 around the axis delta, which is equal to T2 tangential multiplied by the distance T. In this case, distance T is the distance between the point of application of T2 and the point A, which is AB, which is equal to 1 meter. Now T2 tangential, let me specify that this is the positive direction of rotation. T2 will rotate around A in the positive direction. Now this is the radial direction, and the tangential direction would be like this. So now we need to use a bit of geometry in order to determine this angle. So notice that this line is parallel to this line, we suppose. Why? Because here they are telling us, in order to maintain the beam in equilibrium while making an angle alpha is equal to 60 degrees with the horizontal, we attach to a horizontal string. So this is a horizontal string. So this is the horizontal, this is the horizontal. These two are parallel to each other. If this is alpha, this angle here eventually will be pi by 2 minus alpha. Okay? So always in such type of exercises, consider parallel lines and the corresponding and alternating interior angles. So this will be cosine pi by 2 minus alpha, which is equal to T2 sine alpha. Now the moment of the tension T2 around the axis delta, which is given by T2 sine alpha multiplied by D. Okay, so T2 is the one which is unknown, will be kept as a variable. Now sine alpha is equal to sine 60 multiplied by the distance T, which is 1. Now sine 60 is equal to radical 3 over 2. So this is radical 3 over 2 T2. So this is equal to radical 3 over 2 T2. Now as for the moment of the force T1 exerted around delta, which is equal to T1 tangential multiplied by the distance D, and D is equal to, in this case, AC, between the point of application of T1 and the point A, which is equal to, okay, we don't have the value of AC, but AC is AB minus CB, which is equal to 1 minus 0.3, which is equal to 0.7 meters. Now T1 tangential, T1 will try to rotate the system in the negative direction, multiplied by T1. So this is the tangential direction, like this. So if this is alpha, then this is pi by 2 minus alpha, then this is alpha. Okay? Now T1 cosine alpha, which is the projection of T1 along the tangential direction. Now the moment of T1 delta equal to minus T1 cosine alpha multiplied by D, which is equal to minus 100 multiplied by cosine 60, which is half, multiplied by the distance T, which is 0.7. So this is equal to minus 35 Newton meter. Now as for the moment due to the weight around the axis delta is equal to the tangential component of the weight multiplied by D. D in this case is equal to the distance from A to G, because the mass is uniformly distributed. So AG is equal to half AB. Then 0.5 meters. Now the weight tangential is equal to, notice that it will try to rotate the beam in the negative direction, minus the magnitude times cosine. So here it is the same. So this is the tangential direction. So this is alpha, this is pi by 2 minus alpha, and this is alpha, because W and T1 they are parallel. So this will be cosine alpha So the moment of the weight around delta is equal to minus W cosine alpha multiplied by D, which is equal to minus mg cosine 60 multiplied by D, which is equal to minus 10 multiplied by 10 multiplied by half multiplied by the distance D, which is 0.5. So I think this is 25. So minus 25 Newton meter. And finally, for the moment of the reaction R around delta is equal to 0, line of action of R passing through delta. Okay, so this is 0. Now we are ready to solve for this linear equation. So radical 3 over 2 T2 minus 35 minus 25 is equal to 0. Then rearranging this equation is given by 35 plus 25 multiplied by 2 divided by radical 2. So 35 plus 25 is given by 62 over radical 2, which is equal to 60 multiplied by 2 times radical 2 over 2. So 60 radical 2, which is equal to 84.85. Now everything is expressed in the SI, and T2 represents a force, so this is in Newton. So T2 is equal to 84.85 newtons. Let me check the calculation. Okay, so this is correct. And now in number 3, they are telling us find the characteristics of the reaction at the hinge A. Now let me change this question a bit. Okay, so no, it's okay. So by the characteristics they mean the magnitude. So let me change. Let me okay. Let me change it only to the magnitude. Okay. Now I will clarify type. Let's keep it to the characteristics, and by the characteristics we mean it means the line of action plus direction. So this is the one. Now we need the magnitude and the point of application. Okay, so these are the characteristics. Now the point of application, because it is a contact force, then will be the point A. Now the line of action and the direction, it will be the last thing that we will find. Now let's find the magnitude. Now how come one find the magnitude? The magnitude is given by R, which is given by the square root of Rx square plus Ry square. So once we find the value of Rx and the value of Ry, we can determine the value of R. Rx and Ry can be determined using Newton's second law or equilibrium condition, but for translational. Then let me write at equilibrium. We have that the sum of forces is equal to 0 vector. We have the weight, the tension T1, the tension T2, plus the reaction R equal to 0. Now the directions of these forces are clear, but R is not clear. Independent of the line of action and the direction of R, we will calculate it as if it is simply Rx and Ry. So this is the positive direction of the x-axis, and this is the positive direction of the y-axis. Now projection along the x-axis. This is given by wx plus t1x. So we drop down the vectors, and each vector quantity will carry the label x, plus rx is equal to 0. And we are interested in determining rx. Now wx is 0 because w is completely parallel to the y-axis. T1x is 0 completely parallel to the y-axis. And T2x, so T2 is completely parallel to the x-axis, so it's simply minus T2 plus Rx. So Rx is simply given by minus T2, which is equal to minus 84.85 newtons. So Rx is equal to minus 84.85 newtons. Okay. Now as for the y component, so we drop down the vector quantities. Each vector quantity will carry the label y. Then wy minus t plus t1y plus t2y plus ry, which is equal to 0, and we are interested in determining ry. Now wy is given by, so notice that w is completely lying along the y-axis in the negative direction, it's minus w. As for t1y, it's completely lying along the y direction, so it's minus t1. This has no projection along the y-axis, so plus 0 plus ry. Then ry is given by w plus t1, which is equal to 100. Now the weight is given by m multiplied by g, which is equal to 10 multiplied by 10, which is equal to 100 newtons. So 100 plus 100 is equal to 200 newtons. Then ry is equal to 200 newtons. So now we didn't yet answer the question. Let me refer to this figure to complete the characteristics and to explain what is meant by Rx and Ry. So here let me write Rx is equal to minus 84.85 newtons and Ry is equal to 200 newtons, and let me explain what is meant by the reaction at the hinge. So according to our choice, this is positive direction of the x-axis, and this is the y-axis. This is the positive direction, and this is the positive direction of y. So if Rx is equal to minus 84.85 newtons, so Rx equal to minus 84.85 newtons, for sure represented according to some scale. Now Ry will be somewhere here, so Ry is positive and it's given by 200 newtons, so it will be somewhere here. So this is Ry, which is equal to 200 newtons. Then how come we can construct R? So simply we can connect these two like this. Then this will be the reaction R. It has a line of action which is, so the line of action and the direction, the line of action is oblique, the direction is upward to the left. Now we can determine this angle. So what is the value of this angle? So suppose this is the angle theta, then tangent theta, which is equal to opposite. So if this is the hypotenuse, then it will be equal to opposite over adjacent, so which is, so this is theta, then tangent theta equal to the opposite over the adjacent. Now the opposite is this one, which is the value of Ry, which is given by 200, and the adjacent, don't worry about the minus sign, we'll take the positive, which is given by 84.85. You can calculate the value of this angle, then shift tangent will obtain the value of theta. But now don't worry about it. But the line of action, the line of action is oblique, the direction upward to the left. As for the magnitude, can be calculated here like this. Rx to the power 2 is given by 84.85 to the power 2. And you can plug this on the calculator. Then it's given by 217.25 newtons. Okay, so it seems it's a bit difficult, but as long as we follow the specified steps, it is easy. Now recall that we have determined Rx and Ry without worrying about the direction and the line of action of R. Then after we have determined Rx and Ry, including their positive and negative sign, we can construct the vector. And recall that R can be written now in the vector notation, which is given by minus 84.85 multiplied by the unit vector I plus 200 multiplied by the unit vector j, and we know how to represent such a vector. Okay, so that's it for me in this video, guys. In the next part we'll complete solving exercises on this chapter.